When we're discussing about conservative forces, or maybe simply a conservative vector, we always get into towards various elements in physics, like talking one of the main branches of, for example, I'm taking for electrodynamics. Um and this is one of the most fundamental part, that how the Poisson's equation, and I mean, what was the thought process of the derivation of different things, which gets connected towards as we move forward, like the Poisson's equation, Laplace equation, one of the most important and one of the most fundamental that everyone has heard, and many things more, like the so-called electric potential, right? So yeah, let's see. So as we know that electric field is nothing but conservative in nature, right? All of us knows that this is actually conservative in nature. So for conservative force, as we know that the line integral of the conservative force should be equivalent to 0, which later tends towards by the Navier-Stokes theorem that the nabla cross E would be always coming to be 0, right? Okay. So basically from this point only, if we get into the line integral of E dot dl along the curve C, we can notice one thing, that this is nothing else but the work done. How? If I multiply it by Q. Okay, and think it like this now. If I'm making it as q dot e, as this is a scalar, or maybe you can treat it as a constant, so as you also know that it will not affect the integral, I'm moving forward, dot dl. This is nothing else but the work done, and the work done in a conservative field. Okay, if this is a conservative field, and if the conservative force, if the field force is doing work, we know that it will always cause the decrease in potential energy. If the initial potential energy was, let's say, u, then this will be u minus du. So the net change in energy, as we can see, is basically minus du. So this will cause the change in potential energy as minus du. Okay, so from this point, okay, so from this point, I can say that this is a vector. Okay, electric field dot dl could be written as minus du by q. Why I'm taking this side as q, or else this would be the same analysis which we have already, I mean, we all have discussed about the ideology, or I mean the analogy about the force conservation, the energy conservation in a conservative field when we are dealing with different kinds of forces, right? In this case, if we want to make something new, that was nothing but the electric field, we are taking q towards the right hand side and making this as e dot dl instead of the force dot dl, right? This is nothing else but the line integral of electric field, right? Okay, so later on, this dq over q was regarded to be dv, and this was the point from where the term voltage was introduced, and actually it was a kind of necessity to introduce it. Okay, so yeah, for our understanding, we can assume it as a necessity, or maybe we can. Okay, it's up to you, right? Yeah. So if I want to analyze the electric field with respect to a scalar, okay, in all the three dimensions about x, y, and z, using the reverse theorem, I can name it as the nabla of v, right? I can name it as the nabla of v. How? If I'll see, then electric field could be written as minus of du over dl, right? But in this case, it's contradictory, right? So that's why I am taking it as a parameter in x, y, and z in all the three axes. Okay. So from this side only, electric field was concluded to be minus of nabla of v. Okay, and yep. This was the thing. And if I do some mischief in this process, like if I will take the divergence of electric field on both the sides, let's take it. Yeah. So this will lead to the Laplacian operator, that is the double nabla of V. And if we observe it, then this is nothing but Q over epsilon naught. Sorry, rho over epsilon naught. That represents the volumetric charge density, right? And yeah, from this point only, if I see, then this is nothing else but the second or maybe the differential form of Gauss's law, right? Gauss's law states that the closed loop, the integral of the closed loop, or maybe the electric flux dA, is always equivalent to Q over epsilon naught, right? So yeah, from here only we can relate the following things, that minus of nabla, double nabla of V, is regarded as the rho by epsilon naught, where rho is the volumetric charge density, and this was the point, and this is regarded as Poisson's equation. Laplace equation is actually the set of Poisson's equation, which states that when the double nabla of V, consider this only, when this is equivalent to zero, in that case, yeah, it's very much logical that the volumetric charge density must be zero, since epsilon naught can't be zero, right? It's always greater than equal to one, even if we consider it as the relative charge, relative dielectric constant, right? So this would be always equivalent to zero. So basically, Poisson's equation, from here only, Poisson's equation leads to a case in all the three dimensions, taking the double partial derivative, we are getting to be zero. This represents that the volumetric charge density must be zero in case if the double nabla of V is equivalent to zero. So yeah, this was the point from where Laplace equation was concluded. Basically, it all started from a thought process that the electric field can be observed in conservative in nature, and this is how it works.